All right, as the final installment for this Lecture 8 series, I'm going to relate linear momentum to angular momentum, and we'll do a little algebra concerning an angular momentum chart. Then afterwards, we'll do a little bit of exploration of rotational kinetic energy. The stuff in this video will be more in detail than you'll be responsible for on any assessment. In particular, the relationship between linear and angular momentum and velocity will not show up on an assessment, nor will rotational kinetic energy. The angular momentum algebra might show up, but this is more just to kind of wrap up this unit and complete the concepts, not necessarily add material for you to be assessed on. Okay, so let's take a look at an example where we have a rod attached to a hinge. So this is free to spin around in a circle, this green bar around the hinge, but it's stationary to start with. It has length L and mass 2m. And then we have just a ball with mass m that's moving to the left toward the end of it with velocity v to the left. So after some time, this ball is going to hit it and stick to the end, and they will, as we know just intuitively, rotate together counterclockwise, right? This ball will hit, and if it sticks, then they will rotate around. It's fixed at the hinge, so they cannot move overall to the right or the left. They have to stay put and rotate around. So the angular momentum chart for this would be pretty simple. If we ignore the rotation, it would just be one ball that collides with something that is fixed. So there would really be an external force that is causing the momentum to go down to 0. We could also look at the detailed linear momentum of the ball going around in a circle. And we know that requires a force that is directed toward the center. So that's one way we looked at this type of thing in the past. But now let's just use our new angular momentum vocabulary and methods to solve this, our new model. So the first thing is, why does this ball have angular momentum? It's moving in a straight line. Well, let's take a look. If we draw let's use orange. If we draw the position vector from the hinge, so here's our hinge, to the ball, we have some angle that it makes, right? So we'll call that theta. There's some angle that it makes. Over time, this position vector is going to move to the left, right? It's moving in a line to the left, so this angle will shrink. So we do have some delta theta in this direction. What direction? Well, we can use our right-hand rule. This, from our perspective, it's counterclockwise, or that would be out of the page. Right, so we do have some delta theta. And if we have a delta theta, well, angular velocity is just delta theta over delta t. And if we have angular velocity, we definitely have angular momentum. So this ball does have angular momentum about this hinge. But we don't know necessarily what that is. What we do have is our linear velocity, this v. So the relationship between those two is that our angular velocity is just equal to our linear velocity over the perpendicular distance from the axis of rotation. And what do I mean by perpendicular distance? Well, if this orange vector here is our distance, r, perpendicular is the distance that is perpendicular to the velocity. So since our velocity is in the x direction, let's break down our radius vector, or position vector, into a parallel component and a perpendicular component. Right? So this would be our parallel. We don't care about that. And our perpendicular, we do care about that. And since we know that this length is L, our perpendicular is just equal to L, because the ball is traveling in a straight line and it's going to hit the end of this rod. So when we're trying to figure out the angular velocity, the only thing that matters is the r perpendicular. Kind of like when we're figuring out a torque, the only thing that matters is the r perpendicular or the f perpendicular. So I won't prove this, but just take my word for it, and it does make sense that, well, it's conserved. Neither the velocity of the ball before the collision nor the perpendicular distance, this L, is changing, and we would want our angular velocity, our angular momentum, to be constant, conserved, because there's no external torque, right? There's nothing that's causing this rotation to speed up or slow down or change directions in any way. Great. So what is the other ingredient for our angular momentum? Well, we need our rotational inertia. And for the ball, it's pretty simple. There's only one piece, so no sum necessary. It's just mr squared. Its mass is m, but again, for the r, we actually use r perpendicular. I didn't talk about that in lecture because we were only dealing with circular motion, in which case r perpendicular is just r. But the r that's perpendicular to the velocity, again, is just L. So here we'll have m, the mass of the ball, times L squared. And again, this is dependent on whatever hinge we use. So if we had a hinge that was in the middle of this rod, we would have a distance L over 2, and our rotational inertia would be different, and our angular velocity would be different. So this is all dependent on the choice of the hinge or the pivot point, as is the case with all angular velocity and momentum problems. All right, so now that we have our angular velocity and our rotational inertia, we can find our angular momentum. It's just I times omega, and that's going to be equal to V over r perpendicular, which is just L, so V over L times m L squared, which is just equal to V m L. And all of these, I didn't write it, but these are all out of the page. If our delta theta is out of the page, our omega is out of the page, our L is out of the page. So there's our angular momentum of the ball. But now let's think about this in the context of a collision problem, which it is. This ball is going to hit this rod, and if there's no external torques, which there are not, the pivot can apply external force, but not torque, because it has no distance from itself. So using the language that we used with linear momentum, this ball is going to share some of its angular momentum with this rod, right? It's going to hit and stick, and then they'll both rotate together. So the total angular momentum is conserved. This is our total. This isn't going anywhere. But now, instead of just belonging to the ball, it's going to be split between the ball and the newly rotating rod. So we can make a momentum chart for that, an angular momentum chart. We have Li, delta L, and L final. And we have our ball, our rod, and our total. Okay. First things first, there's no total delta L because there's no net torque. What else do we know? Well, we know the initial angular momentum of the ball is out of the page, like we said. And we solve for what that is. It's this VML. And the rod is initially stationary, so there is 0 angular momentum. And so our total initial is just some out of the page, which means that our final is the same, right? Our total angular momentum is conserved, and that is just some vector out of the page. The other thing we know, remember in linear collision problems, when two things stick together, we know that their final velocity is the same. So that same thing is going to be true here, where omega final of the ball is equal to omega final of the rod. The rate at which they're both circling around here, their angular velocities are going to be equal because they're stuck together. So that means that the direction of their motion is the same. So if our total is out of the page, and these are both moving in the same direction, we know that their final angular momentum are also both out of the page. which we could figure out intuitively too, right? If this ball hits this rod and they're both circling around, then clearly that's a counterclockwise. We use the right-hand rule. Those are both out of the page. So now let's look at the rod. If we went from 0 to out of the page, our delta L had to be, well, out of the page. Now for the ball, this is one of the shortcomings of just using these into and out of the page vectors without any accompanying arrows, is that we can't really see magnitude. But what we do know is that in our delta L column, we need whatever the delta L is for the ball plus that of the rod has to equal 0. So if the rod is out of the page, the ball's change must be into the page. An equal and opposite change in angular momentum for the ball and the rod. That doesn't completely reverse the direction of the angular velocity of the ball, right? Its angular momentum either. It just reduces it. So some initial angular momentum out of the page, it loses some, shares it with the rod, and then finally the ball has less angular momentum than it had to start with because it shared it with the rod, but they're both now moving in the with the same direction of angular momentum, and their total is the same as what the ball had initially. So that's the story that our angular momentum chart tells. Now let's go ahead and do the algebra, see what our equations tell us. So let's use this final column here. And I guess the picture I drew doesn't really tell us, or the table I drew here doesn't really tell us that much. We just have out plus out equals out. But we know that each one of these has an accompanying expression. We know that our L final total, this one here, is the same as our L initial total, right? That's equal to this, which we already solved for, is just VML. Because the ball is the only thing with angular momentum to start with, and angular momentum is conserved, so whatever it had to start is the total throughout the whole time. So now we know what L final total is. L final total is also equal to the sum of the final angular momentum of the ball and the rod. That's equal to L final ball plus L final rod. And that's equal to the rotational inertia of the ball times omega final plus the rotational inertia of the rod times omega final. The key here being that these are the same omega final, right? We said because they're stuck together, they have the same omega final. So instead of having two separate omega final ball and an omega final rod, I have just one value that they share. So now we have this neat equation. L final total is this, VML, and it's also equal to this, I ball plus I rod. We also have the information, so we already know that the I of the ball, so let's say I ball here, is ml squared. And I'll give us that the I of the rod, rotational inertia of the rod, is 1/3 ml squared. So you need calculus to figure this out, but anything more complicated than just point objects, I will always give us the rotational inertia, which turns out to be this. And this is important to note, this is a rod with the hinge at the end of it. If the hinge was in the middle, we know that would be a different rotational inertia. This is dependent, as is all of this problem, on where the hinge point is. Okay, so and if we plug that in, the only change, as I said, the rod had a mass of 2m, right? This is 2m and length L, so this is equal to 2/3 ml squared, based on the specific problem. Okay, so now I can set my two expressions for L final total equal to each other. So on one side I have VML, and on the other I have I ball, which is ml squared, times omega final, plus I rod, which is 2/3 ml squared, times omega final. And now we have an expression that we can, or an equation that we can solve for what omega final is. Now my omega final, just doing some simplifications, the m's all go away. This L cancels one factor of L on each side. So it turns out that omega final, well actually I won't skip steps here. So now with these cancellations we have now V equals L omega final plus 2/3 L omega final, and 1 omega final plus, 1 L omega final plus 2/3 L omega final is 5/3 L omega final. And then we can rearrange this so that omega final equals 3/5 V over L. So if we look back at our initial setup, our initial velocity was just V over R perpendicular, or V over L, our initial angular velocity. So omega initial for the ball was V over L. And now our omega final is 3/5 V over L. So omega final is smaller than omega initial, which makes sense, right? Because the ball had some initial angular velocity, and it had to share its angular momentum with the rod. So the final angular velocity of those two combined must be slower than the ball was moving initially. So I think that makes sense. Okay, final thing I said we were going to do, let's look at kinetic energy. So kinetic energy for linear momentum, or linear movement, is just 1/2 mv squared. Right? And let me draw like a little delineation here. 1/2 mv squared. Just like the trend has been with all of our rotational stuff, our rotational mass, so let's say KE rotation. So now we're looking at kinetic energy, or rotational kinetic energy. We have 1/2. Instead of mass, we have rotational mass, which is I, our rotational inertia. And instead of velocity, we have angular velocity, which is our omega. So now here's our rotational kinetic energy expression. That wasn't really a proof, but again, that's much more complicated. We're not responsible for that, but the units work out, and this is correct for our rotational kinetic energy. So let's look at our KE initial. So first our initial, KE rotational initial. The rod is not moving, so that's just the initial kinetic energy, rotational kinetic energy of the ball. So we have 1/2. I of the ball was just ml squared, and the initial omega was just V over L. So we square that. And so our initial rotational kinetic energy, the L squareds cancel, is just 1/2 mv squared, which is the same as we would get for our linear kinetic energy because, well, yeah, that makes sense because we're just changing the way we describe this setup, not changing any physics. Okay, and now for our final, we have KE rotational final is just the sum of that of the ball plus that of the rod, which is now moving. So for the ball, we have 1/2, again, its I is ml squared, and its final omega is 3/5 V over L squared. And then for the rod, its I, we said, is 2/3 ml squared, and it has the same final rotational velocity, 3/5 V over L squared. Okay, so here we have 9 over 25, so we have 9 over 50 mv squared, right? The L's cancel, and for this term we have that same quantity but times 2/3, so that's going to be 18 over 150 times mv squared. And 18 over 150, we can simplify that so it also has the same denominator, so divide each one by 3, so this is 6 over 50. So 9 plus 6 is 15 over 50 mv squared, which is equal to 3/10 mv squared. And if we compare that to our initial, which was 1/2 mv squared, we see that this is less than our initial rotational kinetic energy. So what happened was we lost some. And why is that? Well, this collision was inelastic, right? These two things collided, and since they stuck together, some of that kinetic energy was transferred into thermal energy, sound, whatever. But some of it was transferred from kinetic to other forms of energy. So the process of looking at kinetic energy is very similar to that for linear, except of course now our expression just subs out the rotational values for mass and velocity.